Okay, recap where we stopped previously. Previously, we look at one of the crystal structure. We have three types of main crystal structure, right? You still remember? We have three types of crystal structure. One is BCC, FCC, and HCP. Okay. Of course, when it comes to test, you need to write the full name for the three crystal structure. Okay, we have body-centered, face-centered, and hexagonal closed pack. So today we will go through, we will try to cover another two. Then we'll do analysis on the crystal structure. Previously, we do have a few calculation on BCC. So today we'll repeat the same calculation for FCC and HCP. Okay, previously what we did, we calculate the number of atoms packed together. Okay, we use one equation. Okay, so we calculate in one cube inside BCC, we know that we have two atoms. Okay, we have two atoms because four at the top, four at the bottom. Each one is quarter, quarter, quarter. So we combine, we get two atoms. Okay, so top four, you combine, you get half sphere. You combine these four, you get another half sphere. You combine top and bottom, you get one sphere, and center one sphere. Total is two. Calculation is this one. 1 plus 8 times 1 over 8. Then also we calculate a CP pack. We also calculate the relationship between the A and R. Pay attention to how we do for BCC. Later we do FCC and HCP will be different. BCC, we cut diagonal section from the top. We cut like that. Okay. Then we calculate where is the A and the R relationship. We get A equal to 4R divided by square root of 3. This one, when it comes to your tests and final exam, we assume we already know this relationship already. Okay, so there will be high chances we ask you to prove that particular number. Okay, okay. So for BCC, and then we already calculate the atomic pack factor. We take volume divided by volume. On the top, we take volume of the number of atoms inside the cube divided by volume of the unit cell. So this one, volume of the unit cell is A cube because each side is A. But we use the previous equation where we link the A and R to convert and then to cancel the R on the top. Right, then we get one number. Okay, because volume, this one we use volume. One sphere is 4 over 3 pi r cube, right? Pi r cube, right? So you need to cancel the r term. So you need to transform the A into R term that you derive from this one. Okay, you need to use this one. And each type of crystal structure have different ratio, different A to R. Later we will see FCC. Now it's BCC. We'll use the same method, but the calculation will be a bit different a bit. Okay, again, BCC we chop from half from top. We chop like that. Okay, we chop half like that. Okay, and we calculated APF or atomic packing factor for BCC is 0.68, fixed already, this number. Okay, meaning maybe it come to test or final exam, it tell you are given, let's say, copper, then you're given a table, then given in a table, it give you the APF number. So from APF number, you calculate the radius of that atom, for example. Okay, you reverse back the calculation. So this one already done for BCC. Now today we look at FCC. So we have a few type of drawing, same crystal structure, but few type of structure. First is the hard sphere. Hard sphere will help you to count number of atoms inside the cube. Because again, you need to calculate the APF, the atomic packing factor. You need number of atoms within the cube. So this drawing will help you to calculate the number of atoms inside the cube. Then the second one, reduced sphere. This one help you to do analysis for A and R. A and R. Then this one is the more realistic one where you view under microscope. Okay, so before we going into the calculation, how many atoms inside this FCC cube? You pack like watermelon or snooker ball. You pack. Now what is FCC? FCC is that you have each atom at each 6, so you have 6 atoms at the center of the space. Once you pack and then you chop in the cube size, then you combine all the remaining cube or remaining shape. So how many atoms you have inside FCC? What do you think? How many complete sphere that you can get from FCC? It's like building a Lego. So you look at this hard sphere. So you combine all these spheres together. You have on each face, there's no atom at the center. You have atom at the center of this one, and then you chop. Can you imagine the atom, how they pack? Can, right? So this one is half sphere. Half sphere, half sphere, half sphere, half sphere. Top also half, bottom also half. So how many big circle like this? How many you have? You have 1, 2, 3, 4, 5, 6, right? Yeah. You have 6 half sphere, right? 6, right? Because you have 6 face, you chop face, 6 face, Center one. You look at this center, this center molecule, this center particles, atom. You chop half, so you have 6 faces. So you have 3 complete sphere already. What about the side, the top? Top is half sphere. This add in this 4, you get half sphere. Then bottom another half, so you get 1. All right, like that, you join. So how many you have? 4 atom for complete sphere for FCC. Yeah, so this one will help you to imagine how many sphere you have. Or this one, if you imagine it's good, then this one already can help you already. But this one will help you to imagine. Okay? Okay. Now, again, there are 3 types of drawing: atomic size, hard sphere, and reduced and isolated unit cell. Okay. You know how to calculate APF, right? How to calculate APF? Divide by. Okay. So now what is missing is the A and R relationship. Let's look at how it do. This one, I will not show you how to do it, but there's a number for you to refer. Very high chances this one will come out in test or final exam. Okay, I give you hints already. It's not inside my slides, but there's a question there highlight for you. Okay, now we have 4 atoms that we explained just now already. So this one, no issue. How you calculate? 1/8 times 6/2. Right, so you get 4 atoms. Okay, 4 atoms. Now we try to calculate the relationship between the A and R. Previously, BCC, we chop half from the center, from the top. But now we focus on this face and not chop half. We just only look at this face only. This face, here to here is R. Here to here is 2R. This is 1R. Here to here, you have 4R, correct? You have 4R. R, 2R, R. So total 4R. How to get this one? Trigonometry. Here to here, A. Here to here, A. This is the right triangular. So how to find hypotenuse? Square this one, square root, you get this one. Then this one equal this one. You can get relationship between A and R. You move square root of 2 to another side. Then you can find APF. You'll get 0.7 something. Okay? So your A is 4R divided by square root of 2. Any question on this one? Makes sense, right? Important is you understand how to get A equal to that one. Yeah. APF is 0.74. You calculate. Okay. So they previously will show you the table of type of metals that have certain type of crystal structure. So you refer to that table. So example of FCC, famous one will be aluminium, copper, lead, nickel, and ferrum. Okay. So when you study about chapter 3, you should able to give example, at least 3 example for each type of crystal structure. At least 3 example. Right? So memorize 3 type of metals that fall into BCC. Now we study FCC. Study about type, memorize that one. Or sometimes you can see in the table. So the next one is HCP, hexagonal cross spec. What is hexagonal cross spec? You can see from the diagram here. You have 1, 2, 3, 4. You have 7 atoms at the top, 7 atoms at the bottom, 3 at the center of the crystal structure. 7, 7, 3 at the center. Okay. How to arrange? You go back. You put a tennis ball together, or egg is too dangerous lah. But you put a ping pong ball or something, then you can form something like this. Okay. Now, for example, how to read this diagram? This is 7, right? 1, 2, 3, 4, 5, 6, 7. You have 6 surrounding 1 at the center. So 1, 2, 3, 4, 5, 6 with 1 at the center. This is at the top. Okay. Then this is bottom. This is at the bottom. Same. Repeat the same layer. At the center, you see 2, right? Another one at the back. Is 3. Okay, means 7. Squeeze 3 at the center. Okay, this is HCP crystal structure. Again, there are 3 ways of illustrating HCP. Okay, you have atomic, hard sphere, isolated. For HCP, again, HCP, you have 7, 7, 3 or 7, 3, 7. 737 aircraft. Right? So 7 top, 7, 7, 3 at the center, 7 at the bottom. So when we do calculation, we break the HCP crystal structure in this form. So at the top, you join you get 1, 2, 3, 4, 5, 6 triangular. You draw 3 line, and then you join, you'll get 1, 2, 3, 4, 5, 6, 6 triangular. Same as the bottom. You join center cube to center cube. These 3, you can temporarily ignore them first because they are at the center of the 7 balls, right? They're the center. So this is the A for HCP. This is the A. Whereas the C is the height of the structure. And then there's a numbering. There's a numbering. You take the first, this is a parallelogram or sphere, right? Parallelogram. So 1, 1, 2, 2. Same, you join. The angle from 2 to 2 is 120, and then this is 60. So this one, I don't ask you in test because it's a bit complex. But this one, the APF is the lowest one compared to BCC and FCC. Okay. Okay. 1 Newton is called coordinate number, CN, coordinate number 12. So you see, both HCP, FCC structure is atoms surrounded by 12 other atoms. So both structure have coordinate number of 12. What does it mean? This might be a bit difficult. I go back to the diagram. Okay, this one later when we come to coordinate number. Coordinate number is one atom, like how many surrounding that particular atoms inside the structure. That one later I will explain. APF for HCP, remember this number 0.74. But I won't ask you to prove, but it's good to remember this number. Okay, this is how you calculate the total of number inside the HCP. Okay, so if I label 1, this is 1, 1, and this is 1 and 1. So if you only looking at 1, it will contribute 1/6 of the unit cell. What does it mean? If you look at this atom, 1 is this atom, right? So this atom, when you chop in this sphere, when you chop with this angle, this atom can break into 6. Right? 1, 2, 3, 4, 5, 6. So this center atom at the top, this center atom, it can break into 6 parts. It chop into 6 because of this 6 triangular. Make sense? For atom number 1. Same with this one. This one, another, you can say another prism, another hexagonal shape combined. Okay. Let me draw from the top. Draw from the top. Let's say this is the first prism that you look at. Okay, this is first prism. And then now you look at this atom. Now, by the side also, you repeat the same crystal structure. Then you repeat. This number one outside, this one, also 1/6. 1, 2, 3, 4, 5, 6. Makes sense. Okay. Okay. Yeah. So number one break into 6. Number 2 also break number 6. This is on the top only. Bottom one also same because 6, 6, same. Now what about number 2? This one, number 2, it will 1/12. How 1/12 come into place? Those at the side, this one, this one, it break into 6, right? 1, 2, 3, 4, 5, 6. What about another prisma that put on the top? You have to consider another one that put on the top. There's another set. This 1, 2, 3 repeat at the top. So it got 6 divided by 12, another 6. This one. Okay. But anyway, this one you need time to imagine a little bit, right? You try to play with your ping pong ball or snorkels, all right? Then only you can see is 1/6 or is 1/8. Okay. So how to count? You have 4, 1, 2, 3, 4. So 4, 1/6. You have 1, 2, 3, 4, 1/12. Total, you have 1 atom inside this long cube. Okay. Item number 3 will be slightly run away from the standard alignment. So we count at number 3, this one, that fall into the one of the phase, because you have 6 phase. 1, 2, 3, 4, 5, 6, 6 phase of the side phase. But you only occupied 3 phase only. So this one become, you combine these 3, you get 1. Right? Okay. So this one a bit complex. Okay, this one need time to digest. Time to digest. Okay. C/A ratio. This C/A ratio is 1.633. There is a mathematic way to prove this A to C with the angle, but we are not going there. Just just there's the same calculation. You take A and then sum this what, how many length of 1 to 2, and then you do the equal here and there, and then you get 1.6. Okay. Now, what is important is, again, you're able to identify what mean by cubic. Cubic means all the angle is 90 degree. Most of the case in your final and assessment, we will stay at cubic case. Okay, then the rest, hexagonal, tetragonal, and the rest is outside the scope of this module. But it's good to show you that actually there's other crystal structure there. Okay. Now, this is how HCP, they are being packed in the sequence. So this one is layer A, layer B, layer A, layer B, layer A. This is called stacking sequence. Okay, this sequence will give you a certain shape of that material. If you cut that crystal structure, if you break it like salt, you'll get salt NaCl, you'll get cube shape. But this is one another type. Okay, so this is okay. So the stacking sequence in this case, you can label as AB, 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 and so on. Okay, so this is how you describe that stacking sequence. Layer A by layer B, layer A, layer B, layer A. This is called stacking sequence. Okay. So let's look at one example. Like, how do we ask you in test or final exam? How do we assess your understanding? So you are given a volume of, calculate the volume of zinc crystal structure by using following data. Pure zinc has HCP crystal structure with lattice constant A and C. Find the volume of large cell. So this is how we apply all the calculation for HCP. So you're given this table most of the time. So you're given zinc. Zinc is this one. Zinc value, lattice constant, you have A and C that I showed you just now. Your A is 0.225, C is 0.4947. What is atomic radius? 0.133. C over A is 0.856. Okay, so this 4 number is important in the following calculation. So you need to find the volume. Okay, find the volume. You need to recall back the previous slides about the HCP crystal structure. This way. So you break the top into 6 triangular. You have 6 corner. You join the line together. You get 6 triangular. Then we only interested in parallelogram shape. We take center, side, front, side. So you get a parallelogram shape. You take the top parallelogram, you join, become 1. You know that this is A. This height is C. So again, is calculate lah. So from the top, A will be like that. And you start to do the parallelogram mathematic proving. So if you look at triangular A, B, and C, you know that this is A. This is A, 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 and A. So A, C to A is small a. This is H. So you know that this is rectangular. So each circle, each side is 60 degrees. The total angle of triangular is 180. You divide by 3. Each corner is 60. Okay. So from here, you're able to find the relationship between A and H. So area of the base for unit cell is the area of ABCD. So we want to find this area. So this is triangular area, right? So this is this part. You have two triangular. This, you know how to calculate area for triangular, right? Yeah. This one times this one divided by half, right? Then you have two. So actually it's this one times this one. Make sense? So 2 times half H times A. So actually you get back HA. Right? But you can link the relationship between H and A, right? H, you use a sign because this is your this is H, this is A, this is the angle. You have the in front and hypotenuse is a sine relationship, right? This angle opposite hypotenuse, you got sine. Sine 60 equal to H divided by A, right? Make sense? So you rewrite the equation H equal to A sine 60. Because we want to remove, we can either use A or UH. In this case, we remove H. Because inside here, there's no H. Inside the question here, no H. So we want to remove H parameter. Substitute H, you get double A square sine 60 equal to the volume, not volume, area of the base. So you get the base, you time the height, you get the volume. So A square sine 60 times the CC is the height, you get the volume of the unit cell for HCP. Okay, I try to understand the mathematics, how they calculate. Yeah, nothing complex here, nothing complex. Only you need to recall back how to calculate the area of a equal side triangular. Okay. So you substitute your C value, A value, you get one number. Right? A value is given, C value only the unit is in nanometer. Okay, unit is in nanometer. So you get nanometer bracket 3 lah. Is nanometer. Okay, so this is a reference answer lah. Sometimes the reference answer wrong also, but the step is correct lah. Okay. All right, now A already solved, and we have all the A answer. So the volume for the HCP is 0.03 nanometer cube. Volume of the large cell, we will take 3 because in earlier statement in HCP we have 3 atoms inside this crystal structure. Okay, so the answer is this one. You times the number lah. Okay, I think this one wrong. No 3. This one remove. This one times this one equal to 0.9. Okay, remove the 3 times in the water answer. This one wrong. Okay. All right. For HCP, there's a special definition for large cell and simple cell. Simple cell is the part A. This one. This one. Okay. Okay. All right. We have a short break. Okay, we have a short break. 5 minutes. Is it? No? 5 minutes. Continue 255.